For decades, we imagined the edge of our solar system as empty space where the sun's influence simply fades away. Two aging spacecraft have now proven that picture completely wrong. NASA's Voyager 1 and Voyager 2 have crossed into interstellar space and sent back data revealing that the boundary separating us from the galaxy is not quiet, not gradual, and not at all what scientists expected. Instead of a fuzzy transition zone, they found a sharp magnetic wall. Instead of calm emptiness, they discovered compressed plasma running hotter than any model predicted. And instead of the sun's influence ending cleanly, they detected an interaction so energetic, it's forcing researchers to rethink how star systems actually work. In this video, we will explain what Voyager found at this cosmic boundary, why these discoveries challenge fundamental assumptions about our solar system, and what this means for humanity's first steps into the space between stars. Let's get started. When Voyager 1 and Voyager 2 launched in 1977, their primary mission was exploring Jupiter, Saturn, Uranus, and Neptune. That work wrapped up by 1989. But the spacecraft kept going, and mission planners realized they had a chance to do something no probe had ever done: reach the Heliopause, the actual edge where our sun's domain ends. The Heliopause isn't a planetary orbit or an arbitrary distance marker. It's a real physical boundary created by a cosmic tug of war. The sun constantly blasts charged particles outward in all directions. This stream, called the solar wind, races away at roughly 1 million miles per hour. But the sun isn't alone in space. The Milky Way itself is filled with particles, magnetic fields, and radiation left over from exploding stars and other galactic processes. This interstellar medium pushes back against the solar wind. The point where these two forces balance creates a massive bubble around our entire solar system called the heliosphere. The heliopause is the outer skin of that bubble, separating everything controlled by the sun from everything controlled by the galaxy. Before Voyager, scientists had models and theories about what this boundary might look like, but no direct measurements. Some expected a gradual blending zone, hundreds of millions of miles thick, where solar and galactic particles would slowly mix. Others thought the transition would be chaotic and turbulent, with magnetic field lines twisting unpredictably. Most assumed that crossing this threshold would feel like moving through fog, with conditions changing slowly over a vast distance. Voyager proved all of those assumptions wrong. In August 2012, Voyager 1 became the first human-made object to cross the heliopause. The spacecraft was 11.6 billion miles from Earth when its instruments detected something extraordinary. Within just a few weeks, the number of particles arriving from the sun dropped by more than 95%. At the same time, high-energy cosmic rays from outside the solar system surged upward. The transition wasn't gradual. It was sudden, sharp, and unmistakable. Voyager 1 had crossed a real boundary, and the change in environment was immediate. 6 years later, in November 2018, Voyager 2 made the same crossing from a different location. Its instruments confirmed what Voyager 1 had found. The heliopause is narrow, well-defined, and far more structured than anyone expected. The zone where conditions flip from solar-dominated to galaxy-dominated is only about 10 million miles thick. That might sound huge, but at the scale of the solar system, it's incredibly thin. The heliopause is less like a gradual fade and more like a border wall. But the surprises didn't stop there. Just inside the heliopause, both spacecraft detected a region called the heliosheath, where solar wind particles slam into the interstellar medium and compress. Think of it like water hitting a dam. The particles pile up, heat up, and create a layer of superheated plasma. Voyager measured temperatures and particle densities in this region that were far higher than any theoretical model had predicted. In some spots, the plasma was 3 times hotter than scientists thought possible. This discovery revealed that the interaction between our sun and the galaxy is far more violent and energetic than we realized. Even more puzzling was what Voyager found with magnetic fields. Scientists expected the sun's magnetic field and the galaxy's magnetic field to collide at the heliopause at different angles, creating turbulence and tangled field lines. Instead, Voyager detected something strange. The magnetic fields on both sides of the boundary were nearly aligned. They pointed in almost the same direction. This wasn't in any model. It suggests that magnetic fields may be reconnecting or reorganizing themselves across the boundary in ways researchers are still trying to understand. If true, it means the heliopause isn't just a passive barrier. It's actively shaping the magnetic environment on both sides. Voyager's plasma wave instrument, which detects oscillations in charged particles, also made a critical measurement. It revealed that the interstellar medium, the material filling the space between stars is denser than scientists had calculated. The galaxy is pressing harder against the heliosphere than expected. This extra pressure helps explain why the sun's protective bubble isn't perfectly round. Instead, it's compressed on the side facing the direction of the sun's motion through the galaxy and stretched out behind like a comet's tail. The heliosphere isn't a sphere at all. It's more like a bullet or a teardrop, shaped by forces we're only beginning to measure. These findings have forced a major shift in how scientists think about the solar system's edge. For most of history, we defined our solar system by planets. The edge was wherever the last planet orbited. But Voyager has shown that the real boundary is magnetic and dynamic. The heliopause is where the sun's control actually ends, and it shifts depending on solar activity. During periods of high solar wind output, the heliopause expands outward. During quiet periods, it contracts. Voyager happened to cross during a relatively calm phase, but future probes might encounter a very different boundary depending on when they arrive. Understanding this boundary matters far beyond academic curiosity. The heliosphere acts as a shield, deflecting a significant fraction of the high-energy radiation that floods the Milky Way. Galactic cosmic rays, produced by supernova explosions and other violent events, travel through interstellar space at nearly the speed of light. Without the heliosphere, these particles would bombard the inner solar system in much greater numbers. Voyager's measurements showed that cosmic ray levels on the interstellar side of the boundary are roughly 3 times higher than inside the heliosphere. This shielding effect directly impacts how much radiation reaches Earth, influences climate over geological timescales, and affects the safety of astronauts traveling beyond our planet. NASA and other space agencies are planning missions to the Moon, Mars, and potentially deeper into the solar system. Radiation exposure is one of the biggest challenges for these missions. Astronauts on the International Space Station are partially protected by Earth's magnetic field. Travelers heading to Mars or beyond won't have that protection. Voyager's data provides the real-world measurements needed to build accurate radiation models, helping engineers design better shielding and mission planners choose safer routes and timing. There are also longer-term implications tied to the sun's journey through the galaxy. Our solar system isn't stationary. The sun orbits the center of the Milky Way once every 230 million years, and during that orbit, it passes through regions of varying density and magnetic strength. About 60 million years ago, the solar system likely passed through a denser interstellar cloud. When that happens, the extra pressure can compress the heliosphere, allowing more cosmic radiation to penetrate the inner solar system. Some researchers believe these events may have influenced Earth's climate and possibly even mass extinctions. Voyager's measurements give scientists the tools to model how the heliosphere would respond to such encounters, connecting solar system dynamics to long-term planetary evolution. Beyond immediate applications, Voyager's success has strengthened the scientific case for a dedicated interstellar probe. The spacecraft currently exploring the Heliopause were designed in the 1970s with technology from that era. Their instruments are limited in sensitivity, resolution, and data transmission rates. Despite these constraints, they've revealed that interstellar space is far richer and more complex than expected. A modern probe equipped with advanced sensors could measure magnetic field structures, particle distributions, and chemical compositions across a much wider range of conditions. NASA has already proposed concepts for an interstellar probe mission that could launch in the 2030s, travel faster than Voyager, and reach 1,000 astronomical units within 50 years. That's more than 8 times farther than Voyager has traveled, giving scientists a chance to explore the interstellar medium in unprecedented detail. For now, Voyager 1 and Voyager 2 continue their journey. Both spacecraft are running on dwindling power supplies generated by radioactive decay. Engineers have been systematically shutting down non-essential systems to extend their operational lives. Current estimates suggest Voyager 1 will lose the ability to transmit data sometime around 2025, with Voyager 2 following a few years later. Every signal they send back is precious. Each data packet represents a direct measurement from a region of space no other human technology has ever touched. What Voyager has accomplished goes beyond breaking a distance record. These spacecraft have redefined what the solar system actually is. The edge isn't Pluto. It isn't the Kuiper Belt. It's the Heliopause, a magnetic boundary shaped by the ongoing battle between our sun and the Milky Way. Beyond that boundary lies interstellar space, not empty and calm, but structured, dynamic, and filled with forces we're only beginning to understand. Voyager has given humanity its first glimpse of the space between stars, and that space is nothing like we imagined.